Time might be the greatest illusion you have ever experienced. We are about to embark on a journey through 30 astonishing facts that will completely reshape your understanding of reality. You will discover how the universe manipulates time in ways that defy common sense, from black holes that warp decades into seconds to particles that could theoretically move backwards through history. By the end, you will see the flow of time not as a steady river, but as a twisting, relative, and deeply mysterious fabric of the cosmos. What does it truly mean for the past and future to exist all at once? How can your head be aging faster than your feet? Prepare to have everything you thought you knew about time turned upside down. What is the one thing about time you have always wondered but never found an answer for? Your own personal experience with time is not quite what it seems. The very seconds ticking by on your watch are an illusion, a local phenomenon that changes depending on where you are and how fast you are moving. This is not science fiction. It is a proven cornerstone of our universe called time dilation, a direct result of Einstein's theory of relativity. The theory, in its simplest form, tells us that time and space are woven together into a single fabric, and that fabric can be stretched and warped. Two things cause this stretching: gravity and speed. The stronger the gravity you experience, the slower time flows for you, and the faster you move through space, the slower you move through time. This sounds unbelievable, but you rely on a technology every single day that is built around this very fact. The Global Positioning System, or GPS, in your phone or your car uses a network of satellites orbiting high above the Earth. Those satellites are moving at tremendous speeds and are located further from Earth's gravitational pull. Because of this, time actually runs slightly faster for them than it does for us on the ground. The difference is tiny, only a few millionths of a second per day. But if the satellite clocks were not constantly adjusted to account for this, the entire system would fail. Your GPS would be wrong by several miles within just a few hours. This daily, practical necessity is our most direct proof that time is not a universal constant. The universe itself operates with countless different clocks, all ticking at their own unique rates. And if you think that satellite adjustment is a tiny effect, prepare to witness time warp on an almost unimaginable scale. At the edge of a black hole, gravity becomes so powerful that it doesn't just bend time, it twists it into a knot. Picture a brave astronaut in a spacecraft, carefully navigating toward the event horizon of a stellar black hole. This is the point of no return, where the gravitational pull is so immense that not even light can escape. For the astronaut, time feels normal. Their watch ticks forward second by second. They might conduct an experiment that takes 1 hour, but for everyone else watching from a safe distance far away, something truly bizarre is happening. That single hour for the astronaut could stretch out into decades, centuries, or even longer for the distant observers. They would see the astronaut's ship moving in extreme slow motion, its image reddening and fading as light struggles to climb out of the gravitational well. The astronaut completes their 1-hour mission and crosses the horizon, but by the time that light signal reaches the outside universe, civilizations on Earth might have risen and fallen. This is the ultimate consequence of gravity's grip on time. The fabric of space-time is so drastically stretched near the black hole that the flow of time is pulled almost to a standstill from an outside perspective. It creates a cosmic paradox where two realities coexist, one where time passes at a normal rate and another where it has nearly stopped. The relentless stretching of time near a black hole is a local phenomenon, but the entire cosmos is subject to a far grander and more inevitable clock. Our universe, for all its vibrant activity, is ultimately running down. This final fate is known as the heat death, and it is dictated by one of the most unbreakable laws in physics, the second law of thermodynamics. This law states that in any isolated system, things tend to move from a state of order to a state of disorder. Think of a hot cup of coffee left on a table. It does not stay hot, it gradually cools until its temperature matches the room. The heat energy spreads out, becoming diffuse and useless for warming your hands. The entire universe is that same isolated system on a cosmic scale. All the energy concentrated in stars, galaxies, and even in the matter itself is slowly but surely dissipating. Stars will eventually burn out, galaxies will drift apart, and black holes will evaporate over incomprehensible eons. The universe will reach a state of maximum entropy, which is a scientific way of saying a state of ultimate equilibrium. In this final era, the temperature everywhere will be just a fraction of a degree above absolute zero. There will be no hot spots and no cold spots, no stars to create new energy, and no processes that can extract work from this uniform, thin sea of particles. This is where the concept of time as we understand it may become utterly meaningless. Time, in a practical sense, is measured by change, by the progression from one state to another. A clock ticks, a planet orbits, a star burns, but in the heat-death universe, nothing happens. There is no change, there are no before and after states to separate. The cosmic clock, in every meaningful sense, would stop ticking. The arrow of time, which has flown from the Big Bang forward, would finally have no direction left to go. This is not an explosive end, but a quiet, cold, and eternal fading into a state of perfect stillness. That cold, silent end of everything we just pictured presents a profound question. What if the flow of time, that undeniable feeling of a past gone and a future yet to come, is nothing more than a powerful, persistent illusion? This is not just a philosophical thought experiment. It is a serious theory supported by the laws of physics themselves, known as the block universe. In this view, our reality is not a series of moments replacing one another. Instead, the past, present, and future all exist at once, fixed forever within a single, immense four-dimensional block. Think of it like a movie on a DVD. The entire story is already there, complete and unchanging. When you watch the film, you experience it moment by moment, from the opening scene to the final credits. But the scenes you call the future are just as real as the ones you call the past. They are simply located at a different part of the disc. Your consciousness, the act of watching the movie, is what creates the sensation of a flowing present. In the block universe, your birth, you watching this video right now, and every event that will ever happen to you, all exist eternally within this static structure of space-time. This idea emerges directly from Einstein's own work on relativity, which fused space and time into a single entity. If time is truly relative, with different observers disagreeing on what events are simultaneous, then a universal, flowing now cannot be a fundamental feature of reality. The block universe simply does away with this special moment we call the present, treating all moments in time with equal reality. This can feel deeply unsettling. It suggests that your life is a path already carved through the cosmos, a story already written, but it also offers a breathtaking perspective on existence. Every moment of joy, every triumph, every quiet instant of beauty is not lost to the past, but is forever a part of the universe's permanent structure. The future is not an empty void waiting to be filled, but a landscape that is already, in some profound sense, real. So the next time you feel a moment slip away, remember that in the grand scheme of the cosmos, it may not be lost at all. It is simply a fixed point in the vast, timeless block of reality. This mind-bending concept of a timeless block universe has a direct physical consequence for your own body, right here on Earth. The simple act of standing up means your head is aging faster than your feet. This is not a philosophical puzzle, but a genuine, measurable effect of Einstein's general relativity. The theory tells us that gravity slows time down. The closer you are to a massive object, the stronger the gravitational pull, and the slower your clock will tick. Earth is that massive object. Your feet are closer to the planet's center than your head is, by a distance of roughly 5 or 6 feet depending on your height. This means your feet experience a very slightly stronger gravitational pull. As a result, time for your feet passes just a tiny bit slower than time for your head. The difference is incredibly small. Over an entire 80-year lifetime, your head would be about 90 billionths of a second older than your feet. You could never perceive this, of course, but it is undeniably real. Scientists have confirmed it using the most precise clocks ever built, atomic clocks so sensitive they can detect the time difference between two shelves placed one above the other on a bookcase. This proves that the warping of time is not just for astronauts and black holes. It is woven into the fabric of your everyday existence. Your own body contains not one, but a multitude of clocks, each ticking at a subtly different rate from the others, all dictated by the gentle, relentless pull of our planet. Your own body is a collection of clocks ticking at different rates, a living testament to time's flexibility. Yet we all share a universal experience, the undeniable feeling that time moves in one direction only. We remember yesterday, but not tomorrow. A glass shatters on the floor, and its pieces never spontaneously fly back together to form a whole cup. This one-way street of cause and effect is what physicists call the arrow of time, and its direction is governed by a single, powerful concept: entropy. Entropy is essentially the measure of disorder in a system. The universe has a fundamental rule, the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. Things move from order to disorder, from concentration to diffusion. That cup of coffee cools down because the heat energy spreads out into the room. A tidy room naturally becomes messy. The shattered glass has a much higher state of disorder than the intact one, and the universe will always trend toward that higher disorder. This is why we remember the past but not the future. Our memories are formed by physical processes in our brains, processes that increase the overall entropy around us. To have a memory of an event, that event must have contributed to the universe's journey toward greater disorder. The future, by contrast, is a state of even higher entropy that has not yet been reflected in our brain structure. If you were to see a video of a shattered glass reassembling itself, you would instantly know it is being played in reverse. That event violates the fundamental one-way flow of the cosmic clock. The arrow of time is not just a feeling, it is the universe's irreversible march from order to chaos, a process that gives our lives their narrative sequence and makes the past fundamentally different from the future. That one-way arrow of time does not prevent a remarkable loophole in the laws of physics. You can, in fact, travel to the future. The science behind this is not magic, it is the same time dilation we have already explored, pushed to its ultimate extreme. Consider one of the most famous thought experiments in all of physics, the twin paradox. Imagine two identical twins. One remains here on Earth, living a normal life. The other boards a spacecraft capable of traveling at an incredible speed, a significant fraction of the speed of light. The traveling twin embarks on a journey to a distant star and then turns around and comes back. For the twin on the rocket, time passes normally. They might feel as though their trip took, say, 10 years, but when they return and step back onto Earth, they are in for a profound shock. Their Earth-bound sibling is not 10 years older, but decades or even centuries older. The traveling twin has effectively leaped into the future. This is not a trick of perception, it is a direct result of their high-speed travel. According to Einstein's special relativity, the faster you move through space, the slower you move through time relative to a stationary observer. The traveling twins' clock, including their biological aging process, literally ticked more slowly compared to the clock on Earth. This creates a real physical difference in their ages. While we do not yet have spacecraft that can reach such velocities, the principle is unshakable. We have confirmed it with particles in accelerators that decay much more slowly when moving at near light speeds. So, the path to the future is clear, if technologically daunting. All you need is a fast enough ship and the patience to let the universe slow your personal clock while the world you left behind races ahead without you. Traveling to the future is a scientific possibility, but the ultimate origin of time itself presents a far deeper mystery. Most physicists point to a single, cataclysmic event as the beginning of time, the Big Bang. This was not an explosion in a pre-existing space, but the rapid emergence of space and time themselves from an infinitely dense and hot point known as a singularity. At this moment, the very fabric of the cosmos, including the dimension of time, came into being. This leads to a question that might seem logical but is fundamentally flawed. What happened before the Big Bang? The concept of a before requires time to already exist. If time began with the Big Bang, then there was no before in any meaningful sense. It is like asking what is north of the North Pole. The question itself loses its meaning at the boundary. The singularity is the point where all our known laws of physics, including our understanding of cause and effect, completely break down. It represents the ultimate starting point, a temporal edge to reality beyond which we cannot see. So the next time you try to picture a void before creation, remember that you are trying to use the concept of time to describe a state where time did not yet exist. The Big Bang may not just be the beginning of our universe, but the moment the cosmic clock was first wound, starting its relentless and mysterious tick. This revolutionary idea that time is relative shatters the very foundation of what we consider the present moment. For centuries, following the ideas of Isaac Newton, we believed time was an absolute river, flowing at the same rate for everyone and everything in the universe. There was one master clock and a single universal now. Einstein's theory of relativity declared this a profound illusion. He revealed that there is no single now that applies to the entire cosmos. Instead, whether two events happen at the same time depends entirely on your state of motion. Picture a simple scenario on a grand cosmic scale. Imagine a flash of light occurring exactly halfway between two distant observers. If both observers are stationary relative to each other, they will agree the flash happened at the same instant, but now set one of them in motion. If an observer is moving rapidly toward the location of the flash, the light from that event will reach them sooner. From their perspective, the flash happened earlier. For the other observer moving away, the light takes longer to arrive, so they see it happen later. Both observers are correct within their own frames of reference. They will fundamentally disagree on whether that flash was simultaneous with another event, like a clock chiming elsewhere. There is no privileged God's eye view to settle the argument. This is the principle of the relativity of simultaneity, and it means the orderly sequence of past, present, and future is not a global truth but a personal experience. Your now is yours alone, and someone moving at a different speed or in a different gravitational field experiences a completely different slice of the universal timeline. The cosmic present is not a single line sweeping across the universe, but a fractured, personal reality for every particle and every observer. This relativity of the present moment opens the door to an even more radical possibility, one where particles could theoretically move backwards through time. These are tachyons, a hypothetical class of particles that, by their very definition, always travel faster than light. According to the mathematics of Einstein's special relativity, as an object with mass approaches the speed of light, its energy requirements become infinite, making light speed travel impossible for anything we would consider normal matter. Tachyons sidestep this by starting on the other side of the light speed barrier. They are conceived as particles that could never slow down to the speed of light or below, existing only in a state of perpetual superluminal motion. The consequences of this are staggering. The same equations that predict time dilation for sublight speeds suggest that for a tachyonic particle, time would effectively run backwards. From our perspective, a tachyon's journey would appear to move from effect to cause. Imagine a tachyon signal being received before it was ever sent. It would be like seeing the splash of a stone hitting the water an hour before you even threw it. This completely inverts our understanding of causality, the fundamental principle that cause must always come before effect. If tachyons were real and we could harness them, they could be used to send messages into our own past, creating paradoxes that defy logic. What would happen if you used a tachyon transmitter to warn your past self about a mistake, thereby preventing the very event that motivated you to send the warning in the first place? While no tachyon has ever been detected, and most physicists consider them a mathematical curiosity rather than a physical reality, their existence is not explicitly forbidden by our current laws. They remain a powerful thought experiment, demonstrating just how fragile our everyday experience of an orderly, forward-flowing time might be when pushed to the universe's ultimate limits. Even your own sense of the present moment is a fragile illusion. We often think of now as a shared, universal instant, a single slice of reality that everyone across the cosmos experiences simultaneously. But relativity shatters this comforting idea. Your now is not my now if we are moving relative to each other. The present is not a thick, tangible slice of time you can point to, but an infinitely thin, razor's edge that is entirely personal and constantly shifting. Think of two lightning bolts striking the ground at two distant locations. You might see them flash at the exact same instant and declare they happened simultaneously. But an astronaut speeding by in a spaceship, moving toward one strike and away from the other, would see one flash before the other. From their perspective, the events were not simultaneous at all. Both of you are correct within your own frames of reference. There is no cosmic referee to declare one of you wrong, because there is no single, universal clock governing the universe. This means the orderly sequence of past, present, and future is not a fixed structure, but a fluid and personal experience. The now you are feeling as you watch this video is yours alone, a fleeting point that is defined solely by your position and motion in the cosmos. It is a moment so thin it has no duration, a dividing line between a past that is fixed and a future that is already real in the block universe, yet one that can never be truly shared with anyone who is not standing right next to you. This strange fluidity of time finds a bizarre echo in one of the most peculiar discoveries of modern physics, a new form of matter that seems to beat like a clock without ever being wound. These are time crystals, unlike the familiar crystals of quartz or diamond, which have atoms arranged in a repeating pattern in space. Time crystals exhibit a repeating pattern in time itself. Their structure oscillates in a predictable, periodic rhythm, flipping between two or more states, but here is the crucial and mind-bending part. They do this without consuming any energy. Think of a perfectly shaped gelatin dessert jiggling back and forth on a plate forever, without anyone ever touching it and without the jiggling ever slowing down. This defies our most basic intuition. If you set a pendulum swinging, friction and air resistance will eventually bring it to a halt. All motion in our everyday world dissipates energy and stops. A time crystal, however, exists in a stable, perpetual cycle, not because it creates energy from nothing, which would be impossible, but because it is in a special, lowest energy state that forces this endless oscillation. It is a system that has reached its ground state, like a ball resting at the very bottom of a valley, yet it continues to move. This breaks what physicists call time translation symmetry, the idea that the laws of physics are the same at every moment in time. For a time crystal, one moment is not equivalent to the next because its state is constantly, rhythmically changing. It carves a permanent, ticking groove into the fabric of time itself, a groove it cannot escape. This is not a perpetual motion machine, but a new, exotic phase of matter that redefines our understanding of stability and motion, proving that even in its most quiet state, the universe can harbor an eternal, silent heartbeat. Your brain possesses its own personal timekeeper, one that often disagrees with the cold precision of an atomic clock. While physics describes time as a flexible dimension, your mind experiences it as a deeply subjective river, flowing at wildly different speeds depending on your state of being. In a moment of sheer terror, like a car accident, time seems to dilate into slow motion. The world unfolds frame by frame, every detail stark and clear. This is not a physical effect, but a cognitive one. Your brain, in a state of high alert, shifts into overdrive, consuming sensory information at an incredible rate. It creates a denser, richer memory of the event, and upon replaying that memory, the experience feels as though it lasted much longer than the clock would confirm. The opposite occurs in periods of profound boredom or routine. When you perform a monotonous task, your brain enters a kind of efficient autopilot, recording very little new information. An hour spent waiting in a dull, unchanging room can feel like an eternity in the moment, yet when you look back, that same hour leaves almost no memory trace and seems to have vanished in an instant. This is why a childhood summer filled with novel experiences and firsts can feel like a long, golden era, while entire years of adult life can blur together and slip by in what seems like a few months. Your personal timeline is not a steady tick, but a story written by the novelty and emotional weight of your experiences, constantly warping your perception of the one resource that physics insists is so rigidly defined. This warping of personal time perception finds its grandest parallel in the very birth of the cosmos. Moments after the Big Bang, the universe underwent a transformation so violent and rapid it defies all analogy, a period known as cosmic inflation. For a sliver of a second, the fabric of spacetime itself did not just expand. It exploded outward at an exponential rate, stretching from a subatomic speck to a volume larger than our entire observable universe. This was not an expansion of matter and energy into space, but a stretching of the very stage upon which reality plays out. Picture a tiny, intricate pattern drawn on the surface of a balloon. As the balloon inflates to an immense size in an instant, that pattern is stretched and smoothed across a vast area. This is precisely what inflation did to the infant cosmos. It took the primordial quantum fluctuations, the tiny wrinkles in the newborn universe, and stretched them across the entire sky. These stretched wrinkles became the seeds for all the large-scale structure we see today, the gravitational blueprints for galaxies and clusters of galaxies. But inflation did more than just create the cosmic landscape. It may have also wound up the cosmic clock, setting the initial direction for the arrow of time. Before inflation, the universe was likely in a state of near-perfect, homogeneous chaos, a hot, dense soup where entropy was high and the concept of before and after was muddled. The violent, ordered process of inflation carved a deep groove of low entropy into the universe, creating a starkly ordered state from which everything could then evolve. It gave the cosmos a clear starting point, a defined state of low disorder from which it could only progress toward the higher entropy we see around us today. In a very real sense, the reason you remember yesterday and not tomorrow might be a direct consequence of that unimaginable stretching in the universe's first fleeting moments. The same physics that allows you to travel to the future also offers a potential shortcut through the fabric of reality itself. These theoretical tunnels are known as wormholes, or more formally, Einstein-Rosen bridges. In essence, a wormhole is a bridge connecting two distant points in spacetime. Picture the universe as a vast, flat sheet of paper. To get from a point on one side to a point on the other, you would normally have to travel the long way across the entire surface. But if you could fold the paper so those 2 points touched, a wormhole would be a tiny tunnel punching directly through the fold, creating an instant gateway. According to the equations of general relativity, such structures are mathematically possible. They would be like cosmic shortcuts, potentially reducing a journey of millions of light years to a mere step. But the truly astonishing application is not just for space travel, it is for time travel. A traversable wormhole could, in principle, become a time machine. Here is how it might work. Imagine you have a wormhole with two mouths, mouth A and mouth B. You keep mouth A here on Earth. Then you take mouth B on a journey aboard a spaceship that travels at a significant fraction of the speed of light. Due to time dilation, time will pass more slowly for the traveling mouth. After a year-long journey from the perspective of the ship, mouth B returns to Earth. But because of its high-speed travel, let us say 10 years have passed on Earth. Here is the paradox. If you were to look into mouth A, you would see the past, a view of the location where mouth B was 10 years ago. But if you were to step through mouth A, you would not emerge 10 years in the past. You would simply emerge from mouth B in the present, having taken a spatial shortcut. The time machine function comes from the reverse journey. If you step into mouth B, the one that has experienced less time, you would exit from mouth A into Earth's past, specifically 10 years minus 1 year, so 9 years ago. You would have traveled back in time. This creates a stable, two-way tunnel through time itself. Of course, the monumental catch is that keeping a wormhole stable and traversable is believed to require a form of matter with negative energy density, something we have never observed and which may be completely impossible. But the mere theoretical possibility hints that the universe's rulebook might, in its most extreme chapters, allow for pathways not just across space, but directly through the corridors of time. The bizarre potential of wormholes shows us that time might be far more malleable than we ever dreamed. Yet this strangeness extends all the way down to the very smallest scales of reality, where the universe's rulebook is rewritten entirely. In the quantum realm, particles like electrons and photons behave in ways that defy all common sense. An electron is not a tiny, solid ball orbiting a nucleus. Instead, it exists as a cloud of probabilities, a fuzzy haze of potential locations and states. This is the principle of superposition, where a particle can literally be in multiple places or possess multiple properties all at the same exact time. It is only when we actively look, when we measure it, that this cloud of possibilities collapses into one single, definite reality. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone opens the box to observe it. While no cat ever experiences this duality, the underlying quantum principle is absolutely real and has been repeatedly confirmed in laboratories. This has a profound implication for time itself. If a particle's present is undefined until observed, what does that say about the flow of time from past to future? Perhaps the future is also a haze of probabilities, not a single predetermined track. This leads to one of the most staggering interpretations of quantum mechanics, the many worlds theory. It proposes that every time a quantum event has multiple possible outcomes, the universe does not choose just one. Instead, it splits into multiple branches, and each and every possibility actually happens in its own separate, newly created reality. In one branch of the universe, you are watching this video. In another, you decided to click on something else moments ago. In yet another, you never even encountered this channel. According to this view, all possible futures are not just potentialities, they are all equally real, unfolding simultaneously in a vast, ever-branching multiverse. Your consciousness simply follows one path, one timeline, unaware of the infinite other versions of yourself living out every conceivable alternative. The flow of time, then, is not a river flowing in one direction, but an endlessly dividing delta, with every quantum decision creating new streams of reality, each with its own past, present, and future. That branching multiverse of possibilities exists within a cosmos that is itself in constant, relentless motion. We can trace this motion backward to unveil the ultimate birthday of everything. The universe is not static, it is expanding, with galaxies racing away from each other in what astronomers call the Hubble flow. This is not a flight through space, but an expansion of space itself, like raisins in a rising loaf of dough. As the dough expands, every raisin moves away from every other raisin. The farther apart two raisins are, the faster the expanding dough carries them apart. This is precisely what happens with galaxies. By carefully measuring both the distance to galaxies and the speed at which they are receding from us, we can work this cosmic film in reverse. We can rewind the expansion, pulling all those scattered galaxies back together, compressing all of space, time, matter, and energy until we reach the initial singular point. This rewind gives us a number, the age of our universe, 13.8 billion years. This is our ultimate cosmic timescale, the length of the tape from the Big Bang to this very moment. It is a figure derived not from guesswork, but from the direct observation of the cosmos in motion, a measurement that tells us when the great cosmic clock first began to tick. This concept of time as a dimension is not just a metaphor, it is the fundamental architecture of our reality. We are all accustomed to thinking in three dimensions of space: length, width, and height, the coordinates that define where you are in a room. Time is simply the fourth dimension, the coordinate that defines when you are. Einstein's great insight was to fuse these four dimensions into a single, inseparable entity called space-time. Think of it as a vast, four-dimensional fabric. An object's entire existence, from its birth to its death, is not a series of disconnected moments, but a single, continuous thread woven through this fabric. This thread is called its world line. Your own world line began at your birth, and it winds its way through the space-time continuum, marking every location you have ever been at every single moment you were there. Sitting in your chair right now, you are not stationary. You are moving relentlessly along this fourth dimension, your world line progressing forward through time at what we perceive as 1 second per second. Even if you were frozen in place spatially, not moving an inch, you would still be traveling through the time dimension of this cosmic fabric. Your journey through space-time is constant and unceasing, a permanent part of the universe's grand tapestry. This bending of the fourth dimension is a tangible force, one you can measure with a clock on a mountain. The phenomenon of gravitational time dilation means that mass doesn't just pull on objects, it pulls on time itself. A massive body like our Earth creates a depression in the fabric of space-time, a gravity well. The closer you are to the center of that well, the deeper you are within the gravitational field, and the slower time will pass for. This is not a tiny theoretical effect, it is a confirmed reality. Scientists have placed incredibly precise atomic clocks at different altitudes. A clock at sea level, where Earth's gravity is strongest, will tick measurably slower than an identical clock placed on a mountaintop, where the gravity is slightly weaker. Over a single year, the clock on the mountain will be a fraction of a second ahead of the clock at the beach. Your head, again, is literally older than your feet, but this effect scales up to a cosmic level in a way that can determine the fate of a mission. The movie Interstellar provided a stunning, if dramatized, visualization of this. The crew visits a planet orbiting close to a supermassive black hole named Gargantua. The gravitational pull there is so immense that for every single hour the crew spends on that planet's surface, 7 years pass for an astronaut waiting in their ship in a higher orbit. The movie brilliantly captures the human cost of this physics, where a short delay on the planet's surface means returning to a ship where their colleague has aged decades. This is the ultimate expression of a gravity well, a place where space-time is so drastically curved that time becomes a resource as precious as air or water. It reveals a universe where your address in space irrevocably dictates your speed through time. This fundamental conflict between the quantum world and the cosmos of gravity represents the final frontier of physics. We have two magnificent, exquisitely accurate theories that describe our universe, and they are utterly incompatible. General relativity paints a beautiful picture of the large-scale universe, where planets, stars, and galaxies warp the smooth, continuous fabric of space-time, creating the force we know as gravity. It is a cosmic landscape of curves and ripples, yet when we peer into the subatomic realm, quantum mechanics takes over. Here, the world is not smooth and continuous, but a fuzzy, chaotic dance of probabilities and discrete particles. The force of gravity, which holds entire galaxies together, is completely absent from the quantum rulebook. It simply does not fit. This creates a crisis at the extremes of reality, in places like the center of a black hole or the first instant of the Big Bang, where immense gravity meets the quantum scale. Our current laws of physics break down entirely, leaving us with a profound question mark. The quest to resolve this conflict is the search for a theory of quantum gravity, a single framework that can describe the force of gravity using the language of quantum physics. A successful theory would not just be a scientific triumph, it would force us to rewrite our most basic ideas about time. In the smooth spacetime of general relativity, time is a fundamental, flowing dimension. But in the jittery, probabilistic quantum world, time might not be fundamental at all. It could be an emergent property, a collective illusion that arises from the intricate interactions of countless tiny quantum events, much like the temperature of a gas emerges from the frantic motion of its molecules, even though no single molecule has a temperature. Finding this theory is like searching for a universal key, one that can unlock the deepest secrets of existence and reveal what time truly is when the universe is at its most fundamental, granular level. That very disagreement about the timing of a flash of light reveals an even deeper truth about cosmic reality. Take the classic thought experiment involving lightning and a moving train. Two bolts of lightning strike the ground, one at the front of a long train platform and one at the back. A man is standing precisely in the middle of the platform, and because the light from both strikes travels the same distance to reach him, he sees the two flashes at the exact same instant. He correctly concludes the strikes were simultaneous. Now, picture a woman sitting in the exact center of a train car speeding past that platform at nearly the speed of light. At the very moment she passes the man on the platform, the two lightning bolts strike. From her perspective, the story is completely different. She is moving rapidly toward the light coming from the front strike and away from the light coming from the rear strike. Just as you would run into the sound waves from a car horn in front of you more quickly, she intercepts the light from the strike ahead of her before she receives the light from the strike behind her. She sees the forward flash first and the rear flash a moment later. From her moving frame of reference, the two events were not simultaneous at all. The staggering part is this: both the man on the platform and the woman on the train are absolutely correct. There is no cosmic judge to overrule one of them. The man's now, the single slice of time he calls the present, contains two simultaneous flashes. The woman's now at that same location does not. Her present moment is a different slice of the universal block, one where the forward flash has already happened while the rear flash is still in her future. This proves that the present is not a thick, universal wall sweeping across the cosmos. It is a razor-thin, infinitely personal line that depends entirely on how you are moving. The shared, common sense now you feel with people around you is a local illusion, a fragile agreement that holds only as long as you are all at rest relative to one another. Across the vast distances of the universe, with stars and galaxies in constant relative motion, there is no single privileged present moment that connects us all. This cosmic speed limit is not just a rule for light. It is the ultimate traffic law for the entire universe, and it is written into the very fabric of spacetime. Nothing with mass can ever reach the speed of light, let alone exceed it. The reason for this is intimately tied to the nature of time itself. As an object accelerates, its mass effectively increases from the perspective of a stationary observer. The closer it gets to light speed, the more energy is required to push it just a little bit faster. To actually reach the speed of light would require an infinite amount of energy, an obvious impossibility. But something even stranger happens along the way. All that energy poured into increasing speed does not just make the object heavier, it fundamentally alters its relationship with time. Imagine you are on a spacecraft accelerating through the void. Inside your ship, everything feels normal. Your clock ticks at 1 second per second, and you perform an experiment that takes exactly 1 minute. Yet, for mission control back on Earth, watching you through a powerful telescope, a bizarre transformation is occurring. As your velocity climbs, your clock appears to tick more and more slowly. Your 1-minute experiment seems to stretch out, taking longer and longer to complete from their point of view. At 90% of light speed, your clock would be ticking at less than half the rate of Earth. At 99.9% of light speed, for every single day you experience on board, more than 22 days would pass back on Earth. You are not just traveling through space, you are trading motion through space for a slower passage through time. The universe enforces its speed limit by making time itself a variable currency. The faster you move through the spatial dimensions, the slower you are forced to move through the temporal one. This is why light, which travels at the ultimate speed, experiences no time at all. From the perspective of a photon, its moment of creation and its moment of absorption, even if they are billions of light years apart, are simultaneous. It does not age or experience a journey because at the speed of light, time stops completely. Your journey through the cosmos is a constant balancing act between how fast you go through space and how fast you go through time, with the speed of light as the immutable exchange rate. There is no master clock hanging in the void, ticking off seconds for the entire cosmos. This deeply ingrained intuition of a single, universal time is a comforting illusion, one shattered completely by the reality of our relativistic universe. Every single planet, star, and galaxy is its own timekeeper, its clock set by the unique combination of its local gravity and its velocity through the fabric of space-time. Consider our own solar system as a miniature model of this cosmic truth. Time on the surface of Mercury, a small world with weak gravity and a fast orbital speed around the Sun, passes at a slightly different rate than time on the more massive, slower-moving Jupiter. The difference is minuscule, but it is real and measurable with precise instruments. Now expand that view to the scale of the galaxy. A star orbiting close to the supermassive black hole at the Milky Way's heart, trapped in an immense gravitational well, experiences time far more slowly than a lonely star drifting in the sparse galactic outskirts. And beyond our own galaxy, the variations become truly astronomical. A civilization living on a planet in a dense galaxy cluster, where the combined gravity of thousands of galaxies warps space-time, would have a fundamentally different timeline from one in an empty cosmic void. Their history, from the formation of their first cities to their ultimate destiny, would be measured against a clock that ticks slower than ours. This means the epic story of the cosmos cannot be told on a single timeline. There is no definitive answer to the question of what is happening in the universe right now. An event we see through our telescopes from 1 billion light years away, which we call the past, is the present moment for that distant galaxy, and it is a present moment that is flowing at its own distinct and personal rate. The universe does not march to the beat of one drum, but to the cacophony of countless trillions of clocks, each ticking to its own rhythm. That relentless expansion of countless clocks might not be the final chapter, but merely one act in an endless cosmic play. The idea of a definitive beginning and a cold, silent end is challenged by theories of a cyclic universe, a cosmos without true birth or death. One compelling version of this is the Big Bounce. This theory suggests that our universe is not the first, but simply the latest in an infinite series. In this grand cycle, the universe expands from a hot, dense state as we observe, but eventually the collective gravity of all matter and dark energy halts this expansion. The cosmos then begins to contract, slowly at first, then with increasing speed, collapsing back in on itself in a reverse of the Big Bang, often called the Big Crunch. This collapse does not necessarily end in oblivion. Instead, at the moment of maximum compression, a cosmic rebound may occur. the immense energies and densities could trigger a new Big Bang, birthing a fresh universe from the ashes of the old, which then expands, evolves, and contracts once more in an eternal, repeating loop. Time, in this view, loses its absolute starting point. There was no first cycle, and there will be no last. Our entire cosmic history, from the first stars to the last black holes, is just one iteration in an infinite series. Another, even more profound model is conformal cyclic cosmology, proposed by physicists like Roger Penrose. It suggests that our universe is not reborn from a crunch, but rather transforms seamlessly from one eon to the next. In the far, far future, when the universe has expanded to an almost unimaginable scale and all matter has decayed into light, the cosmos becomes vast, cold, and empty. At this point, the concept of scale and distance loses all meaning. An infinite universe and a single point become mathematically identical. This allows the dead, empty end of our universe to become the smooth, high-energy beginning of the next. The universe resets not with a bang, but with a quiet transition where the infinite future of one eon becomes the Big Bang of the next. In this breathtaking vision, the arrow of time is not a one-way street with a clear start and finish, but a continuous, looping path. The end of time is merely a gateway to its own beginning forever. This profound link between time and our own minds forces a startling question. Does time require a conscious observer to exist, or is our consciousness itself a product of time's relentless arrow? This is not just physics, but a deep philosophical puzzle that challenges the very nature of reality. On one hand, our entire experience of life is a sequence of moments, a story told by our brain. Without a mind to perceive the change from one state to the next, can we truly say time is flowing? A rock does not feel the passage of years. A planet does not reminisce about its formation. It is only through conscious awareness that the concepts of past, present, and future have any meaning at all. Some interpretations of quantum mechanics even suggest that the act of observation is what collapses probability into a single reality, seemingly making consciousness an active participant in shaping the timeline. Yet the opposing view is equally compelling. Physicists like Julian Barber propose a radical alternative. He suggests that time is not a fundamental part of the universe, but a complete illusion. In his view, reality is a vast collection of frozen moments, which he calls nows. Each now is a complete, static configuration of the entire universe, containing everything that ever exists in a single, timeless snapshot. Your birth, your first day of school, you listening to this sentence, all of these are just individual, separate nows. They do not flow into one another. There is no past pushing the present into the future. So where does our powerful, undeniable feeling of a flowing time come from? Barber suggests that our consciousness creates this flow. Our brain, as a complex physical system, accesses a sequence of these nows, one after another. Because each now contains a memory of the previous one, we have the sensation of a continuous timeline, much like flipping through the pages of a photo album and perceiving a moving story. In this breathtaking vision, consciousness does not emerge from time. Time emerges from consciousness. We are not passengers on a river of time. We are the ones who create the current, stitching together a universe of eternal, frozen moments into the story of our lives. Your journey through the flowing river of time hits a logical brick wall with an ancient puzzle. Over 2,000 years ago, the Greek philosopher Zeno devised a series of paradoxes designed to prove that motion and change are impossible illusions. The most famous of these involves the legendary hero Achilles in a race against a tortoise. In a show of fairness, Achilles gives the tortoise a head start. Zeno argues that for Achilles to win, he must first reach the point where the tortoise began. But by the time he gets there, the tortoise has moved forward a little. Achilles must then reach that new point, but the tortoise has again advanced. This process repeats infinitely, with Achilles always having to close an ever-shrinking gap, but never quite catching up. According to Zeno, the swift warrior can never overtake the slow tortoise because the distance between them can be divided into an infinite number of points, making the task of traversing them logically impossible. This paradox applies just as powerfully to time itself. To experience an hour, you must first experience half an hour. To experience that half hour, you must first experience a quarter of an hour, and so on, dividing infinitely. How can you ever arrive at a future moment if you must pass through an endless series of smaller and smaller intervals first? The flow of time seems to crumble under the weight of its own infinite divisibility. The solution to this mind-bender arrived with the invention of calculus in the 17th century. Calculus provides the mathematical tools to handle infinity, showing that an infinite series of progressively smaller steps can indeed add up to a finite, measurable whole. The infinite number of gaps between Achilles and the tortoise converge to a finite distance, which Achilles covers in a finite amount of time. The paradox is resolved not by denying the infinite divisibility of space and time, but by proving that an infinite sum can have a finite limit. Yet the solution reveals something even stranger about the nature of reality. It suggests that the timeline we experience is a true continuum, a smooth and unbroken fabric that can be divided an infinite number of times without ever reaching a smallest possible unit. There is no ultimate pixel of time, no tiny cosmic clock tick that is fundamental and indivisible. This continuous nature is what allows for motion and change as we know it, but it also means that within every single second you live, there is literally an eternity of smaller moments, an infinite nesting of instances within instances. The very structure of your life is built upon a foundation that is mathematically endless. That infinite divisibility of time is the silent, patient architect of the cosmos itself. The grand structures we see in the night sky, from brilliant stars to swirling planets, are not instantaneous creations but slow-motion masterpieces sculpted by gravity over almost incomprehensible spans of time. The entire process of star and planet formation is a testament to time's relentless forward-driving arrow. It begins within vast, cold clouds of gas and dust, where the gentle pull of gravity starts a patient dance of collapse. For millions of years, these clouds slowly contract, fragmenting into denser clumps. There is no sudden flash, only a gradual accumulation, a slow gathering of matter under time's patient hand. As a protostar forms at the heart of one of these clumps, the pressure and temperature at its core build for another 100,000 years or more until they finally reach a critical threshold. At that precise moment, nuclear fusion ignites and a star is born. This ignition is not the end of time's work, but a new phase. For a star like our Sun, its main sequence lifetime will be a steady, 10 billion year-long balancing act, with the outward push of fusion energy holding the inward crush of gravity at bay. All the while, in the disk of leftover material surrounding the newborn star, another patient process unfolds: planetary accretion. Tiny dust grains gently collide and stick together, building pebbles, then rocks, then planetesimals over millions of years. These larger bodies' gravitational pull grows, sweeping up more material in a process that is both violent and gradual, eventually assembling the planets of a solar system. The very atoms that make up your body were forged in the heart of a long-dead star and then patiently assembled into a world over eons. Your existence is a direct product of time's unhurried cosmic schedule, a schedule that operates on a scale where 1,000,000 years is but a single, fleeting tick of the clock. This single question of why the Big Bang had such incredibly low entropy is perhaps the most profound mystery in all of physics. The arrow of time, the very reason you remember yesterday and not tomorrow, depends entirely on this initial condition. The universe began in a state of exquisitely fine-tuned order, a hot, dense soup that was, paradoxically, perfectly arranged to allow for everything that followed. Why was it so ordered and not in a state of maximum chaos from the start? The answer is not found in the laws that govern the universe's evolution, but in the mystery of its initial moment. One radical hypothesis points to a multiverse. In this vast ensemble of universes, each with its own random initial properties, it is statistically inevitable that at least one would, by pure chance, begin with the low entropy needed to form stars, planets, and life. We do not live in a special universe. We simply live in one of the rare habitable ones that won the cosmic lottery. A universe where the initial conditions were just right for time to have a clear direction. Another, even more mind-bending idea is cosmological natural selection, which suggests universes can reproduce. In this theory, black holes could act as seeds for new baby universes, budding off into their own space-time domains. A universe that produces more black holes would, in turn, generate more offspring universes. Over many cosmic generations, universes would be naturally selected for the properties that maximize black hole production. And it just so happens that a universe with low initial entropy is exceptionally good at forming stars and consequently black holes. Our universe's orderly beginning might not be a random accident, but the result of a Darwinian process on a cosmic scale, where we are the product of a long line of universe ancestors fine-tuned for fecundity. These ideas push the boundaries of science, suggesting that the reason time flows forward for you today might be rooted in either an infinite cosmic landscape or a timeless cycle of birth and reproduction that spans the multiverse. These silent, rhythmic heartbeats of the universe are no longer just a theoretical marvel. They are a reality being forged in laboratories. Time crystals are a new, non-equilibrium phase of matter, which means they maintain their rhythmic oscillation without ever settling into a quiet, stable state. They are created by researchers using complex systems, like a line of charged atoms called ions, held in place by lasers in a vacuum chamber. Scientists then hit this orderly chain with a pulsing laser, a regular jolt of energy that sets the entire system ticking. In a normal material, this external driving would cause chaotic, unpredictable motion. But in a time crystal, the atoms respond by flipping their magnetic orientation in a rhythm that is a multiple of the laser's pulse. If the laser fires every 10 nanoseconds, the crystal might flip only every 20 nanoseconds, locking into a persistent, stable cycle that does not match the driving force. This breaking of time symmetry is the crystal's defining trait, a clock that ticks to its own slower beat without winding down. The potential of this discovery is staggering, particularly for the field of quantum computing. The fragile quantum states used to store information, known as qubits, are easily disrupted by their environment, causing errors. A time crystal's inherent stability and resistance to disruption could act as a perfect protective framework, a built-in rhythm that shields qubits from decoherence. This represents a tangible breakthrough in our manipulation of time itself, not as a dimension to travel through, but as a property we can engineer and harness, creating materials that beat with an eternal quantum pulse. So we arrive at the final frontier of our journey, not a place in space, but a state of being for the cosmos so profound it challenges the existence of time itself. The universe's ultimate fate, the heat death, is not merely an end of things, but a potential end of meaning for the dimension that defines our lives. After trillions upon trillions of years, when the last black hole has evaporated and all matter has decayed into a faint, uniform sea of radiation, the cosmos will reach a state of maximum entropy. In this final equilibrium, there are no temperature differences, no energy gradients, no stars being born, and no structures forming. Every corner of existence is identical, a perfect, featureless stillness. And in that perfect stillness, what becomes of time? We measure time by change, by the progression from one state to a different one. A second is defined by the oscillations of a cesium atom, a year by our planet's journey around the sun. But in this final era, nothing changes. There is no before and no after, because every state is exactly the same as the one that came before it and the one that will follow. The cosmic clock has no ticks left to count. The arrow of time, which flew from the Big Bang and gave us causality and memory, simply has no direction left to point. Time as a measurable, flowing quantity may simply cease to be. It would be a universe that still exists, but one where the word when has lost all purpose, frozen in an eternal, silent now from which there is no future escape. Our journey through these 30 astonishing facts reveals a cosmos where time is nothing like the steady, universal river we perceive. Your own experience of the present moment is a fragile illusion, a local agreement that shatters across cosmic distances. Gravity warps your personal clock, ensuring your head ages faster than your feet. The universe you call home may be just one iteration in an infinite cycle of cosmic rebirth, and the arrow of time itself is a temporary phenomenon, born from a mysterious state of perfect order at the Big Bang and destined to fade into meaninglessness in the distant heat death. Every second you feel passing is a complex interplay of relativistic physics, quantum uncertainty, and your own conscious mind stitching together a sequence of timeless moments. This is the grand reality, a universe of countless clocks, each ticking to its own rhythm, where the past and future may already be eternally real. We have only scratched the surface of this profound mystery. The cosmos is full of wonders waiting to be unraveled. Tell us in the comments which of these facts about time bent your mind the most, and subscribe to join us on our next exploration into the heart of the universe.